Okay, so our next speaker is Thomas Vidick, and he will tell us about a continuation of a beautiful line of work on area laws and efficient algorithms in 1D.
Thanks, David. The mic is okay, right? All right. So this is joint work with Itai Arad, who was at CQT in Singapore when we performed the work, but he just recently moved to the Technion, and Zef Landau and Umesh Vazirani. So I'm going to tell you about a classical algorithm that, given as input, a local Hamiltonian in one dimension finds a representation for the ground state, or more generally, the low-lying eigenstates of that Hamiltonian. So I hope there's not going to be any confusion compared to the previous talks. So this is a purely static problem. There's not going to be any jumping into black holes in this talk. I'm sorry. So let me just set it up for you. So the input to our problem is going to be a local Hamiltonian. So it's a sum of n terms. Each of the terms, the normalization that I'll use, so each of these hi, think of it as a positive semi-definite matrix. That's not a requirement, it just makes my life easier. The normalization is that it has norm at most 1. So our system looks like this. There's n qubits arranged in a line. Also, everything that I say generalizes to qubits, higher dimensions, but just for the talk, we're going to concentrate on qubits. So you have these n qubits, and your Hamiltonian acts on them in the following way. So you have a first term, which acts on the first 2 qubits, second term, etc., all the way to the end. So this is a nearest neighbor Hamiltonian. Some examples, some of you who come from physics might be familiar with Heisenberg model, AKLT model. AKLT is spin 1. I'm not going to define those, but there's a large class of physical Hamiltonians that fall in this framework. And so in general, if I take my Hamiltonian, it's a Hermitian matrix. Given my normalization, it's going to have eigenvalues that lie between 0 and at most the norm of the Hamiltonian. So the spectrum should have shown up. The spectrum looks something like this. The smallest eigenvalue could be 0, could be not. I'll call it epsilon 0. I'll think of it as something that's close to 0, but could be above. There's a ground state that I'll call gamma, and then there's a bunch of other eigenstates that are spread out around the whole possible range of eigenvalues. And so we're going to focus on the low energy eigenspace. So that's the bottom part of the spectrum. I'll be a little bit more precise what I mean by bottom later on. And the main question that we're interested in is, vaguely, can we map out this low energy eigenspace? So can we find efficient representations? The reason we're interested, so I said this is a static question, right? No evolution, given the Hamiltonian, find representations for the ground state, maybe the first excited state, etc., when you can do it. Okay, so when can we do it? First thing is, if I'm trying to map out this space, I need to be able to represent vectors in there efficiently, and I better restrict myself to cases where at least I know that the space is going to be polynomial dimensional. There's no hope in trying to start making maps or finding bases for exponential dimensional subspaces. So think of this T, the low part of the spectrum, as a tiny part of the whole Hilbert space. And we're trying to argue that this tiny part is going to be a little bit special because our Hamiltonian is local, and we're going to be able to find a description for that chunk of the Hilbert space. So the first set of news is unfortunately bad news, is that if I start with a general Hamiltonian, even under this restricted model, even in fact, if I take a Hamiltonian that's translation invariant, not on qubits, but on qubits, then the problem is QMA hard, even in the case where I only focus on the ground state. So assuming that QMA is different from NP, there does not even exist an efficient polynomial size representation for the ground state of my one-dimensional nearest neighbor Hamiltonian. So there's no efficient representation, so I don't even start thinking about algorithms. Right? Okay, but then physical intuition and proof by Hastings gives us one more structural element that we can impose on the Hamiltonian that is going to guarantee the existence of efficient representations. And this structural element is the existence of a gap in the spectrum. So if you assume that the ground state at ground energy epsilon 0 is well separated from the first excited state, so there's a constant gap between the two lowest possible energies, epsilon 0 and epsilon 1. Remember my normalization. When I say constant, I mean constant. And the normalization is that each term in the Hamiltonian has norm 1. So the total norm of the Hamiltonian is n, right? in that case, it's known that the ground state satisfies an area law, which means that the entanglement across any of the n-1 possible cuts of my system there is a constant. So this is a picture of the area law in 2D. It's easier to visualize in 2D. So if you took a state that's defined on the two-dimensional grid, so these are qubits, and you focus on the region in the middle, in principle, for an arbitrary quantum state, the entanglement entropy between the gray region and the outside could scale as the volume of the region. The area law tells you that ground states of local Hamiltonians that are gapped in one dimension are special in the sense that the entanglement of a region like this scales like the size of the boundary. So this is why it's called area law. In one dimension, boundaries are constant size, so you get constant scaling of the entanglement. So in that sense, the ground state reflects the locality of the Hamiltonian. Entanglement is going to be local in the ground state, but this only holds if you have this assumption of a gap. So if the ground state is well separated from the rest of the spectrum, of all that we know. So this gives you these representations. I'm not going to talk too much about how I represent my states in the talk. It's important in practice, but for our purposes, it won't matter too much. If you care, we're just going to be working with matrix product states that have constant or polynomial bond dimension, right? So the area law implies that there's a matrix product state representation for the ground state where each bond has scaling that's linear in the length of the chain. Even you can make it slightly sublinear. Don't worry too much about this. My measure of entanglement will be the Schmidt rank. So you take your state, you look at any cut, you do the Schmidt decomposition, and you look at the number of non-zero eigenvalues. And that's what I will call Schmidt rank. Sometimes I'll call it bond dimension. All right, so we have efficient representation, and so the next question is, can we find this thing, right? Because your input is pretty small, this Hamiltonian 4x4 matrices, it doesn't take much space. So you have a small representation for your input. Can you find efficient representation for the output, a matrix product state representation of the ground state? And so this is a problem that for which we gave an algorithm a couple years ago with Zef Lando and Umesh Vazirani. So we showed that precisely in the case where the area law applies, so there's a unique ground state and there's a gap about that ground state, then we can find a representation of the ground state in time that is polynomial in the size of the system times some factors that are doubly exponential in the inverse gap. So that's not the best you could do, right? If you think about the area law tells you have an efficient representation. For example, for gaps that scale like 1 by log n, you'd have an efficient representation. Our algorithm would be exponential in that regime. But in the regime where there's a constant gap, it works fine. I'm sorry. And so the work was, this was extended by Chubb and Flamia, I think last year or 2 years ago also. They showed that this can be extended in the same regime for the gap, but even if there's a little bit of degeneracy. So if the ground state is not unique, but there's a logarithmic degeneracy. So let me just summarize the situation a little bit, right? So we have these Hamiltonians. This is what the spectrum looks like in general, and there's different regimes. So if you assume nothing, or if you assume that there's a tiny gap, which the gap is going to appear, but it's tiny. So if you have you know at most that the gap is maybe 1 by poly, then unless QMA is equal to NP, there's no efficient, assuming QMA is not equal to NP, there's no efficient representation for the ground state. Now, if you guarantee a slightly bigger gap, at least let's say 1 over log, bigger, then the area law kicks in and tells you that an efficient representation exists. And if you assume even a bigger gap, then our algorithm, or the extension by Chubb and Flamia kicks in, and then not only is there an efficient representation, but you can find it in polynomial time. I guess the question for this talk is, can we go a little bit further? What's the right boundary between hardness and efficient algorithms? And practice kind of seems to suggest that the algorithms have reached the extent to which they work. So if you think about the kind of algorithms that work in practice, so there's a very efficient heuristic called the DMRG for density matrix renormalization group. This works very well if you have a constant gap and a unique ground state. As soon as the gap closes and you start going to critical systems, and even more so as soon as the degeneracy of the ground space increases, it performs pretty badly because partly because it's not designed for that. So you'll have it find one ground state, and then you need to run it again to find another ground state and kind of exclude the ground state that you had found by adding some large energy penalties. But this has a tendency to make you find more and more entangled ground states. And it, maybe for a constant degeneracy it works, maybe log, but then it starts, who knows what happens. So that's the state of the art, and now let me tell you what these results are about, and then I'll explain the results a little bit more. So we give results algorithms in two incomparable regimes of parameters. So the first one I call DG for degenerate ground space. So we take local 1D Hamiltonian just as before, and now let's assume that there's a gap, but the ground space degeneracy could be basically as big as an algorithm could handle, so polynomial. So something like this, I made it as big as PowerPoint allowed me to do. So this is a polynomial ground space. Then there's a big gap above that polynomial ground space. And under that assumption, then we give almost the best that we could hope for in terms of algorithms. So first of all, we prove an area law because there was no area law for these systems. So we show an area law, meaning that under those assumptions, there exists a basis for the ground space where each state is well approximated by a matrix product state that has Schmidt rank across any one cut, right? That scales as, see, the scaling in terms of the gap is the same as the area law for the case of the unique ground state. And then there's a multiplication factor by the dimension squared of the ground space. Maybe this you could reduce to the dimension of the ground space. I'm not sure. I wouldn't be surprised that this is fairly tight. I don't have any argument that says that it's tight. So that's the first thing. That's the area law. And then the running time of the algorithm, n to the 1 over gap squared. So even if you were only interested in the case of a unique ground state, this is a marked improvement compared to the previous algorithm, right? We went from doubly exponential in the inverse gap to singly exponential in the inverse gap. So this is going to be polynomial as soon as the gap is 1 by square root log n. Not quite 1 by log n, 1 by square root log n. So that's the first setting. Second setting is incomparable setting. I call it LD for low density. We're not going to make any gap assumption anymore. So the only assumption that I'll make is that there is a certain part of the spectrum that I'm interested in between the lowest, the ground state, the lowest eigenvalue, epsilon 0, and some epsilon 1 that is, it's just some parameter that I get to choose. But my assumption is that in between these two values for the energy, there's at most a polynomial number of eigenstates of my Hamiltonian. That's the Hamiltonian. That's the assumption. I need to set one more parameter, mu. Mu is also a parameter that you get to choose. You give to the algorithm, but then the results will depend on mu. So what are the results? The results are that there is going to be an area law, and also the algorithm is going to give you a basis. A basis for what? Not quite the polynomial size space that's between epsilon 0 and epsilon 1, but it's going to force you to lose a little bit, and it's only going to return a basis for the space of eigenvectors whose energies are between epsilon 0 and epsilon 1 minus mu. And the time that is going to take is, well, okay, the time is quasi-polynomial. Okay, I'll get to the time later. The Schmidt rank that we get, so the kind of area law that we prove, is that the entanglement is going to scale, or the bond dimension, n to the 1 by mu, right? So mu, think of it as an artificial gap. This system doesn't have a gap. The only thing is that it doesn't have too many eigenstates at the bottom. And you have to impose an artificial gap, not in the sense that you're changing the Hamiltonian or anything. This is just a parameter you're giving to the algorithm. You're telling it, look, this little window, I'm not asking you for anything, I'm asking you for the stuff below. And how large a window you give it, the lower the entanglement of the vectors that it's going to find. Also, the faster the running time, also I didn't make it quite explicit here. So note that this is not a polynomial algorithm. I mean, there's no gap, so we did what we could. It's a so I guess, right, so I was going to ask if Babai was in the audience, he would know, but okay, right, a quasi-polynomial, right? So we give a quasi-polynomial, we give a quasi-polynomial time algorithm for this case. So that's the result. I mean, anyone wants to raise their hand and ask the question about the result, otherwise I'm going to start explaining a little bit how we go about it. All right, so I'm going to focus mostly on the topmost scenario because it's the easiest to explain, but the algorithm is really essentially the same for both cases. Did you have? No?
So you don't get any eigenvalues in the range, or you might make mistakes in that range?
Yeah, so exactly. So the thing is you can, so the algorithm, you give it parameter.
Could you repeat the question?
The question is, what happens here? So could you make mistakes? So could the algorithm return vectors that lie in here or don't? Something like this. So the point is that the algorithm is going to return to you a subspace that has polynomial dimension, and it has it has a basis that has efficient matrix Pollux state representation. So you can diagonalize the Hamiltonian in that subspace and look at the eigenvectors. And so the guarantee is that every eigenvector below mu will be there. There might be some other stuff. There might even be some stuff that's up there. But it's easy for you to kick it out, right? Because you can solve, yeah. Thanks. All right, so let's go for it. So there's two things I want to tell you about in order to understand this algorithm. First, there's a algorithmic component, which is something that we call approximate ground state projection. This is the, maybe I'll refer to it as the workhorse of the algorithm. So it's the component that does all the work. And then there's a data structure. This data structure, because we're not going to work directly with matrix Pollux states. I mean, at the low level we do, but at the high level, because we're trying to find subspaces, we're going to work with subspaces. And the subspaces we work with, we'll call them variable sets. I explain what these are. And then once we have these two ingredients, we'll put 2 and 2 together and get an algorithm. This algorithm is going to have a tree-like structure that I'm going to explain. So first I explain AGSPs, then variable sets, then tell you how we put them together in order to get an algorithm. Okay, so approximate ground state projection. So this is something that was introduced a while back by Arad, Lando, and Vazirani. They introduced it as a tool, which was a theoretical tool at the time. They used it to give a different proof of the area law that Hastings had proved with improved scaling on some of the parameters. I think mostly the local dimension, so the qubit dimension, they had a better dependence on that using the approximate ground state projection. So let's think about our problem, right? What are we trying to do? We have this Hamiltonian and we're trying to figure out a basis for the low energy space. Just to simplify, let's assume that the minimum energy is 0, like frustration free, just for the exposition. And then I have my first excited state that's at energy gamma, constant above 0. And so my goal is to basically come up with an implementation of the projection on the ground space. So that would be not an approximate, it would just be ground state projection. There's a picture there in case the ground state is unique and you're trying to find a projection that shrinks anything that's orthogonal to the ground state because you don't care about that stuff, but that preserves the ground state. So let's imagine that we're trying to implement this projection efficiently, and this will be a tool in our algorithm. So one way to rewrite exactly what the projection is, this is kind of doing imaginary time evolution. We can write it as the limit as this beta goes to infinity, e to the minus beta h, right? Because given I'm assuming a frustration-free Hamiltonian, this thing is just 1 on the ground space, and then anything above the ground space, it becomes 0, it kills. And so I'm going to do a little back-of-the-envelope calculation here to try to get efficient approximation to this operator as something that we could apply as part of our algorithm. And for this, there's 2 things that we can use about the Hamiltonian, which are my 2 main assumptions. One is that it's a local Hamiltonian. 2 is that it has a spectral gap. So let's start by first using the spectral gap. All right? This is telling us that, back-of-the-envelope calculation, this is telling us that we don't need to go all the way to infinity, right? If we're interested in just preserving the ground space and shrinking stuff that's above the gap, it's enough to take a parameter beta that scales like a large constant, c is a large constant, divided by the gap. And in that case, your ground state space will be preserved. Anything above will be hit by e to the minus at least c, so it'll be hit by a constant factor, it'll be shrunk, right? So you can, up to constant errors, we can make that approximation. And the second step is to use the locality of h to say h is a sum of local terms. I can do a Taylor expansion naively of my exponential, expand all the monomials, and I get a sum of product of terms like this, right? The hi's are local terms. How far do I need to go in my Taylor expansion in order to get something that's a good approximation? Well, as far as the norm of the exponent, what's the size of the exponent? The norm of the Hamiltonian divided by the gap, right? Approximately, there's that constant there, but let's not worry about this. So I need to go in my Taylor expansion to degrees that scale like the norm of the Hamiltonian divided by the gap, right? And then I'll have a decent approximation. So, and if I do this and I call this operator k and I say this is an approximate ground state projector, it's an approximation to my ground state projection, then it has the property that if I start with any state in space that has already a reasonable overlap on the ground space, let's say a half, that's my psi there, and I hit it with the operator k, I just renormalize, then I'm going to get something that's closer, right? Because the component of psi on the ground space will not change. The component that's orthogonal will be hit by some constant that depends to how well I did my approximations, and depending how I set the parameters, I'll get something like this. So I'll argue that this is already pretty good. Why is it good? Because let's think of how application of the operator affects the entanglement or the bond dimension of the vectors that we act on, right? So let's look at this thing. Okay, it's a sum of a bunch of terms. Let's ignore the sum for a little bit. Each term is a product of how many norm of Hamiltonian? Norm of Hamiltonian is n, right, at most, with my normalization, n by gamma. So I have n by gamma terms. That's a lot, right? But these terms are local, so they act on different bonds. And so on average, if I focus on one cut in my chain, how many terms act on it? Well, n by gamma divided by the number of cut divided by n, so just 1 by gamma. So on average, if I apply this product to my matrix product state, each cut is only hit a number of terms that scales like 1 by gamma. Every time I hit it, I'm going to multiply the bond dimension by a constant, and so the Schmidt rank blows up by 2 to the 1 by gamma. This is scaling that's all right, right? I can handle that. That's the scaling that I expect. So this is pretty good. We could maybe try to stop the proof here, QED. I mean, there's a bunch of problems, right? So let's look at what the problems are. I see two problems with this approach. So remember, right, we got this approximation to the ground state. One problem is I hand-waved this summation. I mean, this summation has an exponential number of terms. So it's fine if I'm able to apply one given term, but now I have to sum exponentially many of them. I can't do this, right? I don't have, so the problem is I don't have an efficient representation of this operator as a matrix product operator or something. That's one problem. Second problem is I said, well, if we have this vector that has constant, etc., okay, how do we find this vector that has constant overlap with the ground state in the first place, right? And that's the main difficulty faced by these algorithms. Sort of this approximation, this hand-wavy calculation I did for you is telling you that if you're close to the ground space, then you can improve things fairly efficiently, maybe, assuming we manage to deal with this sum there. The problem is how do you find a constant approximation? And that's the difficulty here. You're kind of, this is how the DMRG works and the previous algorithm works also a little bit. You progress through the chain and you have to be extremely careful, optimizing one qubit at a time and making sure that you have a good approximation to the ground state, and you extend, and you have to be very careful. So the difference in this algorithm is that we're going to be a little bit more rough in the way that we do things, and that's going to give us efficiency improvements. So that was just to explain what the approximate ground state projection does for us. It's not, we don't actually use this Taylor expansion. We use something a little bit more complicated. I might tell you about at the end if I have time. If I don't have time, you can look it up. It's not the main difference in this paper compared to previous works. So the main difference is going to be these variable sets and how we use them. So forget about the approximate ground space projection for a second, and now let's think about how we're going to represent our ground spaces, what kind of data structure the algorithm is going to manipulate. So again, this is my chain of n qubits, and this is what I'm trying to find, right? It's a space of vectors, and each of these vectors is an n qubit state. As I progress through the algorithm, I'm going to be manipulating vectors that are not over the whole chain, but over subsets of qubits, and we're going to extend these subsets of qubits one step at a time. So what I'm going to have is a subspace of vectors like this that lie on the 4 middle qubits. And in order to design an algorithm, in order to quantify progress, I need to have a way to define what it means for this subset S to be a good approximation to the subspace T. And this by itself doesn't mean anything, right? Because S is on 4 qubits, T is on n qubits. How do you define a good approximation? So this is the notion of variable set that we introduce. So we'll say that this small set S is a variable set for the big set T if the following condition holds. If whenever I take a vector in T, there's a way to write it as a tensor product of a vector in S for the 4 qubits, and then on the left and right, I can put anything I want. So anything from the left Hilbert space on the left, anything from the right Hilbert space on the right. If that was my notion, it wouldn't be enough because these are product states. I can't hope to approximate, even mildly entangled vectors using product states. So also I allow linear combinations, right? So that's the definition of a variable set. S is a variable set for T if any vector for T can be represented as a linear combination of stuff that's anything on the left, anything on the right, but in the middle it must come from S. I wrote up mathematical definition of it here if you care, but I think the intuitive definition is good enough. And now let's make a couple observations. Okay, so first of all, our goal is just to come up with a viable set that's defined over the whole chain. Right? If you unwind the distribution and S is defined everywhere, then you're done, right? You've achieved what you wanted to do. You have a set that contains approximation to your whole set T. And now my observations are that, one, if we try to construct sets on a constant number of qubits, then that's pretty easy. For instance, I want to construct a viable set on the first 2 qubits. Let's just take a basis, right? This is going to be 4 states. I put every possible state, and then, of course, they are extendable to approximations of any state in any space. So viable sets on small subsets are easy. Second observation, a little bit harder to see, but not too hard, is that if you take viable sets over 2 neighboring regions, and then you take the tensor product of these sets, so take all pairwise tensor products, then this is again going to be a good viable set defined on a larger set of qubits. The error is going to double, and that's actually not something too bad because you also doubled the number of qubits that the set was defined on. So these 2 operations are easy, and now let's just put these 2 operations together and get an algorithm that starts from 0 and constructs a good approximation to the whole space T. So here's the algorithm. You start with your chain, and initialization uses the first observation. We can, let's say, this doesn't really matter, but I paired the qubits 2 by 2, and for each of them, I choose a 4-dimensional basis, a product basis, anything, and that's my viable sets. And so each of these individually is a viable set for the whole, for the low energy space T. In fact, it's a viable set for any space, right? I haven't used anything. Okay. And now let's try to start combining these things until we get a viable set for T. So I'm going to take them pair by pair, and I take the tensor product, and now I get a space that's defined over 4 qubits at a time. And see, I kept the vectors in green. What I mean by vectors in green means good vectors. They have a low complexity. They're just tensor product. They're product states, easy to represent. The sets, they became red. Why red? Because they became bigger. And that's going to be a problem if I do this too many times, right? The size of my sets, whatever it was before, S, now I take all pairwise tensor products, so it's become S squared. The error, as I said before, doubles, but that's not too bad because the number of qubits doubles. If I do only log steps, that's going to be fine. It's going to blow up by not. But squaring over log steps, that's no good. So this is what we have to focus on now, reducing the size of a viable set. And at that step, I really wish I had something intelligent to say, but I don't. So the only thing that we could come up with in order to reduce the size of these sets is to subsample. So take a random subspace. This is too big, take a random subspace. How small? Some ratio of the dimension. In order for my parameters to work out later, I divided the dimension by S times, I hope you can see, I can't even really see, but I divided by S times D squared. D is a parameter that's going to come in later. So I just, subsampled a random subspace of relative dimension 1 by S D squared. So that reduced the size, right? Obviously, I did this really heavy-handedly, but then what happens to the error? Terrible, right? I had an error that was close to 0, now it becomes close to 1. If I had a vector, I knew that I had a basis in there that had pretty close to 1 overlaps with my space T. You can work it out because whatever you divided the dimension by, this is what the overlaps are going to get divided by. So now I have terrible overlaps. Terrible, not so terrible. So if you think of these dimensions as being constants throughout the regime of the algorithm, then 1 minus this error is a constant close to 1. And so this is where we're going to use the AGSP. We're going to apply this matrix product operator, that's a good approximation to the ground state projection, in order to improve the error. And so now things become green. So 2 things happened here. The vectors became green because they become better approximations to the ground state as I apply this operator. The set became a little bit bigger, and that's something I won't have time to go into, but because when I define this approximate ground state projection, it's an operator that's defined over the whole chain, right? But now I'm applying it on a subset of the chain, so I have to define what this means. How do I cut my operator so that it's meaningful to apply it on a subset? Well, I have to cut it, I have to talk about the bond dimension of the MPO, and I kind of have to do all possible ways of cutting it up, and this is why the size of the set is going to improve. But the error also improves, and so the key point in designing this AGSP is you want the trade-off to be favorable, right? How much does the size improve? How much does the the size increase, how much does the error improve, and your goal is to design an operator that is such that, okay, you go back basically to the same parameters that you had on the first step. If you manage to do that, well, you can just continue, go on forever. In fact, you couldn't go on forever because I'm hiding under the rug the complexity of these vectors as matrix product states. This is going to increase, so you have to worry about that too, but I don't have time to go into the details. So that's the structure of the algorithm. We just repeat this for log n times, combining these sets pairs by pairs. And in the end, we'd end up with a polynomial size set of vectors that have polynomial size representations. And then we just, depending on what we were asked for, we return the R. R is a parameter of the algorithm, lowest energy eigenvectors. And one interesting thing about this algorithm is that most of the parameters, you can really think of them as being constants. So this is not something like DMRG or something that manipulates very close inverse polynomial approximations to the ground state or the ground space because you're worried about errors. We're not worried about errors. We have this tool, the AGSP, that tells us that as long as you remain within a regime of constant approximations, you can improve these approximations. And we're using that repeatedly throughout the algorithm. So I was going to say a little bit more about the AGSPs, but sorry, I'm skipping that. I'm out of time. I'll just conclude. So let me give you a little bit summary of what we did. So what we give are new area laws. I didn't really focus on too much on that, but both of the settings that I described, there were no area laws before, and so the area laws come as a corollary of the algorithms. So for these two scenarios that I described, the case where there's a constant gap and then a degenerate ground space up to polynomial degeneracy, that's the scaling of the area law in that case. It's pretty good. The case where there's no gap, and you can see this critical kind of scaling of the area law that you expect in that regime. A few features of the algorithm that I went over. One thing that's interesting is this tree-like procedure. Another interesting thing I think that we would be nice to elaborate on more is the data structure that's used. I said at the bottom level, we do use matrix product state representations for the bases for these variable sets. I think it would be interesting to try to figure out if we can get rid of MPS altogether and use something like maybe a MERA or something like this that's directly adapted to representing subspaces, not vectors inside a subspace. This I mentioned already. Some interesting questions. One question that's interesting is, okay, I'm talking about efficient polynomial time algorithms, okay, but that's theory. What does it do in practice? And we have some interesting preliminary results there. So I've been working with people at Caltech, especially Brendan Roberts, who's a PhD student in condensed matter physics group at Caltech. He's implemented this algorithm, and I thought maybe this thing would run on like 4 qubits or something, but he's done impressive work, and it works very well. You can solve systems on 100, 200, 500 qubits, depends on the system, of course, and it compares favorably with DMRG. Like on the easiest cases, it's slower, but on cases that are hard for DMRG, then it's like some comparable, which I think is impressive given how much work has been put into optimizing a DMRG. So that's work in progress that I think is interesting. Interesting open question is whether we could get a polynomial time algorithm under this low density assumption that we had. Ours is quasi-polynomial. There's no hardness result there. It could be that we can find a polynomial time algorithm, and maybe in order to achieve it, we'd have to improve the way we represent vectors or variable sets. And this is just, the obvious open question is, okay, can you do any of this in higher dimensions? That's a hard question, but I think it's an interesting question. Okay, so I'll stop here.
Questions for Thomas?
In higher dimension, can you use these ideas even to give a heuristic algorithm? I mean, one where you can't prove it, but it's worth trying?
I mean, there's many problems in high dimensions, right? Because there's even the problem that, if you have a PEPS, it's not clear that you can compute the energy and stuff like that. One thing that is nice about this algorithm is that there is a natural way to at least get started, in the sense that if you'd have a 2D grid, you'd say, let me, chop it up into squares and start putting these squares together, and let's see what happens, right? I don't know what happens. One of the difficulties is that the AGSP constructions, these we don't quite know how to do. Again, for the same reasons that you can't, you'd have an MPO in 2D and an MPS, and you can't do efficiently these contractions. So we very quickly lose track of what happens. I think one thing that is interesting that we're planning to try is, at least now that we have something numerically that works in 1D, is because DMRG also you use in 2D and you do this snaking stuff. Here we don't have to do the snaking stuff. We can do this, squares and put them together, but I don't know what is going to happen.
Yes, Norbert.
I think he wants a mic.
Does a method allow you to say something about the structure of the low-lying states, like that they say differ only locally from the ground state and things like that?
What do you mean by that? So, for instance, if I take my ground space and I take the reduced densities on half the chain, then these would be sort of lower dimensional because they tend to be similar? Or? Oh, no, you meant the ground state and the low-lying eigenstate.
If you can solve for the low-lying excitations, there's a gap above that. Can you make some statement how those look like? Like, often one would assume they're kind of local excitations on top of the ground state and things like that.
Not that I know, because we don't obtain them as functions of the ground state. We just really create the whole space together, and so they're treated all together as, a polynomial number. So it's not like we do like DMRG does, for instance, right? It's not like we'd find the ground state and then say, okay, let's look for the other guys by doing tweaks or something. We find everyone.
Okay, so it's not clear if this space has some extra structure, kind of.
We're not using explicitly.
Okay.
No, yeah. I guess it's a question.
Okay, thanks.
More questions?
So I know you said you didn't want to talk about black holes, but it's a little striking that.
Let's take that offline, Ning.
It's actually striking that the LD condition that you have is actually one of, I think maps exactly onto one of the known necessary conditions for a conformal field theory to have a classical gravity tool. So it may be interesting to analyze what it means, like what this allows you to say for conformal field theories that possibly have gravity tools.
Yeah, so I don't know much about CFTs, but it is a natural assumption. I mean, we're definitely not the first ones to consider that assumption. I know there's also many variations on that assumption, so you have to be a little bit, like it. For instance, sometimes, like we impose it globally, sometimes this assumption is also made locally, like on restrict, we don't do that. Yeah.
I was pretty interested in the connection with Mera. So does this also give a quantum circuit to prepare the ground state or the swept space?
I mean, it gives a classical algorithm to prepare it. So definitely it also gives a quantum. I mean, as soon as once you have the matrix product state, you have an algorithm to prepare it. So you mean maybe in a sense, I'm not sure. Do you mean would it give a natural quantum algorithm? So let's see, there's operations that because the main algorithmic step is applying this approximate ground state projection, and that's represented as an MP. So it's doing imaginary time, it's doing some approximate version. So numerically, the way we do it is Trotter expansion and these kinds of things. So you could imagine, I guess, doing that algorithmically. I'm not sure I'm answering your question, though.
I think we could talk later.
Okay, sure.
Thanks.
I think there's time for one more question, if we have one. Otherwise, let's...
No, I think...
Oh, there is one? Oh.
Maybe finding a whole basis vectors for the low energy spaces or overkill. Can you improve it immediately for local observables?
Oh, what do you mean by that? So I would want to just estimate a local observable on a, but if the space is degenerate, so what is that? So in that case, what? I want to sort of figure out the range of values it could take on the ground space, for instance?
For instance, yeah.
Yeah, so that's a good question. I don't know that we can do better. I don't know. Yeah, it's an interesting question. Another kind of question we could ask is, because I said, oh, you need this space to be polynomial dimensional. You don't, right? The space could be higher dimension, and then you'd just be asking to find one vector there or two vectors or something like this. So I don't know how to do that Actually, in fact, even if you give me a degenerate ground space, but you tell me I only care about one vector, can you do it fast? I can't. Like I have to, or our algorithm cannot. So it has to find the whole basis in order to keep the things under control. So.
Okay, let's thank Thomas again and break for lunch.